Hello, Math 2 students. I hope you're ready to take a walk down memory lane back to the first section of the Math 2 textbook. In that first section, we learned about vertex form of an absolute value function. And there was an equation that looks like this: f of x equals a times the absolute value of x minus h plus k. And what we learned about that equation was the a value would tell you whether or not the v-shaped graph would open up or down, and whether or not the v-shaped graph would have a vertical stretch or shrink in comparison to the parent function. We also learned that the vertex of the v-shaped graph was h comma k. And we learned that this negative sign is a little tricky because your h value ends up having the opposite sign of the number that you're looking at inside the absolute value. And we also learned that the axis of symmetry is x equals h, or x equals the x coordinate of the vertex. So this is a symmetrical graph where the left side of the v-shaped graph is exactly a mirror image of the right side of the v-shaped graph. In order to graph the parent function, what you need to do is go 1 to the right and up 1, because the absolute value of 1 is 1. Go 2 to the right and up 2, because the absolute value of 2 is 2. 3 to the right and up 3, because the absolute value of 3 is 3. 1 to the left and up 1, because the absolute value of negative 1 is positive 1. 2 to the left and up 2, because the absolute value of negative 2 is positive 2. And 3 to the left and up 3, because the absolute value of negative 3 is positive 3. Now, today, we are going to move forward to vertex form of a quadratic function. And if you can remember what we learned in the first section of the textbook, what we're learning today about this equation is the same thing. There's only a slight difference between the graphs. This is a V-shaped graph, and this is a graph that's a smooth curve that's called a parabola. So, the absolute value function says a equals the absolute value of x minus h plus k. The quadratic function says a times, and these are parentheses now, x minus h squared plus k. In the absolute value function, the a tells you if it will open up or down and stretch or shrink. In the quadratic function, the a value tells you whether it's going to open up or down or stretch or shrink in comparison to the parent function. The vertex is the same. If you're looking at an absolute value function, the vertex is h comma k. And if you're looking at a quadratic function, the vertex is h comma k. Also, the axis of symmetry is the same. It's x equals whatever the x coordinate of the vertex is. And a parabola is a symmetrical graph where the right-hand side and the left-hand side are mirror images of each other. So one of the main differences is how you need to make the graph. Because this is a V-shaped graph, these sides make perfectly straight lines. So really you only need the vertex and one point on this side to draw that line, and the vertex and one point on this side to draw this side of the V-shaped graph. In a parabola, that will not work. So if I put this point here at the vertex and this point here at 1, 1, then if I drew a line through there, it wouldn't go through these other points on my parabola. So a parabola is a curve. It's not made of straight lines. So if you use a straight ruler and you try to graph it by only drawing a line through 2 of the points, you will not draw the parabola. So you need to be able to plot more points on your graph to make an accurate graph of a parabola. Now we're going to look at an example and see actually how do we make a graph of a quadratic function when the equation is in vertex form. But we're going to start with more familiar territory. We're going to take a look at this graph right here, the graph g of x equals negative 2 times the absolute value of x minus 3 plus 4. Step number 1 is to identify what your a, your h, and your k values are. So our a value is -2. Our h value is +3. That's not a mistake. It is +3. And our k value is 4. So our vertex is h comma k. So our vertex is 3 comma 4. And now we need to graph 3 points. So the first point that I'm going to graph is going to be the vertex. So I'm going to go 3 to the right. And then I'm going to graph this thing by thinking about what the parent function would look like if the parent function was graphed opening down and with a vertical stretch of 2. So I'm going to put the vertex here and think of what would it look like if it opened down and had a vertical stretch of 2. So I would go 1 to the left and down 1. But if it has a vertical stretch of 2, I'm going to go 1 to the left and down 2. And so that'll give me a point right here. And I know that my axis of symmetry is going to look like this. So there's going to be a symmetrical point on the other side of the axis of symmetry right here. So that is all of the points that I need to make this graph. Because the V-shaped absolute value graph is made up of 2 straight lines. So if I put 1 straight line here and 1 straight line here, that is enough information to see what the graph looks like. Now, the quadratic function, what the lesson is really on today, is more complicated, but it starts out exactly the same way. Our a value is -2. Our h value is +3. Yes, that's right, it's +3. And our k value is 4, which makes our vertex 3, 4. And so now we need to graph at least 5 points. The reason that we need more than 5 points is our graph is not going to be made out of straight lines. Our graph's going to be made out of a curve. And so a ruler cannot draw a curve by drawing a line through 2 points. So first I'm going to go over 3 and up 4. And there's my vertex. And when I look at my a value, I know it's going to open down and I know it's going to have a vertical stretch of 2. So normally when I graph the parent function of a quadratic function, I start at the origin and it opens up. I'm going to think about what it would look like if I started at that vertex and it opened down. So normally I would go over 1 and down 1. But because it's a vertical stretch of 2, I'm going to go over 1 and down 2. Now, my axis of symmetry is right here. So I know there's going to be a point on the other side of the axis of symmetry right there. And so what some students would do, this would be a big mistake, is they would just take a ruler and they would make a V-shaped graph. But quadratic functions don't make V-shaped graphs. Quadratic functions make parabolas. So we're going to have to keep going. So now if I was graphing the parent function and I went over 2, I would go down 4. But because I have a vertical stretch of 2, when I go over 2, I'm actually going to go down 1, 2, 3, 4, 5, 6, 7, 8. Now on the other side of the axis of symmetry, there's going to be a point in that exact same spot. So that's going to be right there. So now when I go to make the graph, if I were to use a ruler, it wouldn't work. I can't make a line through all of the points by using a ruler. I'm going to have to make this thing look like a curve. So it's going to look like this. And there's our curved parabola. Now I want to show you one more thing. Some students do not like making graphs by thinking about the parent function or about a vertical stretch or vertical shrink. So they use an alternate method. What they do is they just make part of a table. But you might like this method when I show you, because parabolas are symmetrical. You actually don't have to make the whole table. You just have to make half of it and the other side is going to be the same. So here's how that would work. If I wanted to make a table, I would have x and y. And the big difference from the tables that we made earlier this year is we're going to want to put right in the middle of our table, that's where we want to put the vertex. So our vertex has a 3 for its x coordinate and a 4 for its y coordinate. Now, all we want to do is symmetrically move out from that point wider and wider, just like the parabola gets wider and wider. So 1 to the right of 3 is 4, and 1 to the left of 3 is 2. 1 to the right of 4 is 5, and 1 to the left of 2 is 1. So if we figure out these two places on the table, we will automatically know that this one is going to match that one, and this one is going to match that one. Because we can see on a parabola, here's our vertex, and then there's 2 points that match, and then there's 2 more points that match. So I'm going to take my vertex form. So I have f of x equals -2 times empty bracket minus 3 squared plus 4. And you might be surprised at how easy this is to figure out in your head. If I put 1 in the empty bracket, I have 1 minus 3, which is -2. -2 squared is 4. 4 times -2 is -8. So this is -8 plus 4 is -4. So I know that's -4. That's this point right here. We already put it on the graph, even though we used a different method. And if that point is at -4, its symmetrical point on the other side has to be at -4 also. That's this point. All right, if I put 2 in the empty bracket, now I have 2 take away 3, which is -1. -1 squared is +1. +1 times -2 is -2. And -2 plus 4 is 2. So 2, 2, that's this point right here that we already have on our parabola. And its symmetrical partner over here is 4, 2. That's that point right there. So you can either think about the parent function and the vertical stretch or shrink, or you can make a table the way that I did here. The key thing about making the table is if you put 5 points there and you put the vertex in the middle and then you make it symmetrical. So if you put a 3 here, 1 to the left is 2. 1 to the right is 1. And so you make this the very middle of your symmetrical parabola, and then when you calculate 2 of the y values, you'll automatically get the other 2 y values for free. So that is how you graph a quadratic function if the equation is in vertex form.